Okay, so this module is on 2D flow and LaPlace's equation. And these are the learning, I want you to pay attention to these learning objectives because they tell you the levels we got. So you should be able to derive LaPlace's equation in groundwater for 3D flow. And all it takes is using Darcy's equation and the continuity equation. We're going to do it for 2D in class. And doing it in 3 dimensions is just an extension of that. And then I want you to be able to describe both the potential function and the flow function and what they are and how they can form a solution, which leads directly to be able to describe what equipotential and flow lines are and their relationship. I say that you need to draw a flow net for 2D confined flow with the boundary conditions, but what I really want you to do is be able to, given a flow net, drawing flow nets is a tedious process which we don't do much anymore because we have nice numerical solutions that do it very easily for us. But having a flow net is a really good way to interpret the information. So you need to be able to interpret a flow net, use the flow net. I think that might be on the next page, is it? Yes. No. That last bullet is the most important. Given a properly constructed flow net and the soil properties, you need to be able to interpret it. I'm not going to ask you to draw any flow nets in this class. We will talk about transform sections and how to deal with hydraulic continuity that's anisotropic. We just got through last lesson talking about why we almost always have a different horizontal hydraulic connectivity than a vertical hydraulic connectivity. So it's a very, very common situation to have, and I'll show you how to deal with that. All right, so let's derive LaPlace's equation. So I'm going to start with my elemental area here. That's dz by dx. Only this time we're not talking about stress, we're talking about flow. So I have coming into the left side Vx, and I have coming down from the top Vz. So if I want to know what's happening, we're going to use continuity here in a second. So if I have Vx coming in the left-hand side, what do I have coming out on the right-hand side? Well, I got the Vx that went in, plus whatever change in flow there is, which is the partial of Vx with respect to x times dx. Right? The rate of change in the x direction is times dx. And in the vertical direction, I have the similar thing. I got Vz coming in, I have Vz going out, plus the rate of change of the vertical velocity as a function of z times dz. Right? So if I'm going to apply continuity, and if I have saturated material, and if there's no volume change, what can we say? So the continuity of these solutions all for saturated material, no volume change. Qn is equal to Q out. One of my favorite things. There's a lot of politicians that need to learn some of these simple conservation rules. All right? Qn is equal to Q out. So that's what continuity is. So Qn, what's Qn? Qn is Vz times dz, right? Dz is we're assuming this thing is 1 unit into the board, right? Or 1 unit into cyberspace. I can say that now, that's kind of cool. 1 unit into cyberspace. So it's V times the area, which is just dz, plus Vz dx, right? And Q out, so that's Q in, right? In this direction I have Vz times dx, and in this direction I got Vx times dz. All right, well, what's coming out? Well, what's coming out is the flow on the x side, which is Vx times the partial of Vx with respect to dx times dx, all times dz, which is the area, right? And coming out the bottom, I got the flow out the bottom, Vz times the partial of Vz with respect to dz times dz, all times dx. And I'm going to let Q in equal to Q out because we got a saturated material that's not changing in volume, it's not swelling, it's not shrinking, so I just add all those together. And I can start getting rid of a lot of stuff here, right? So all I did was add those two equations together. And this simplifies pretty easily. If you look at that, the Vx's are going to cancel out. The Vz's are going to cancel out. And I'm just going to be left with this partial differential equation. Very simple partial differential equation. So that's continuity. There it is right there. There's your continuity equation. All I've done is provide conservation of mass. Qn is equal to Q out. All right, so what's the other flow rule that we just learned that's really important? It has to do with mustard. Darcy's law, thank you very much. So now we're going to apply Darcy's law. All right? Oh, I'm sorry, I'm going to simplify this first by dividing by through dz. Sorry about that. Don't tell the mathematicians that we did this, but we're going to divide by dz and dx. Now we're going to apply Darcy's law. Okay, Darcy's law is that Q equals KIA, or the velocity is equal to minus K times I. Now, last time we didn't throw the minus sign in there, but we got to be careful to think about this. Does water flow from high head to low head or low head to high head? High to low, so we have to have a negative, before we just knew that the water was coming out of the, we knew what direction the flow was, so we didn't think about it too much. But here, it's not going to be obvious which direction the flow is, so we got to be really careful about our signs. It's the velocity is minus K, because the gradient is going to be the change in head, and the flow is opposite the change in head, because it goes from high to low and not from low to high. Okay. So the velocity in the x direction is the hydraulic conductivity in the x direction times the hydraulic gradient in the x direction. But what is the hydraulic gradient? The hydraulic gradient is the change in head over a given flow length. So that's really just dh dx. The instantaneous hydraulic head any place is just in the x direction is just a change in head with respect to x. So it's just dh dx. Right, are you with me? There's a pretty simple change there. And obviously in the z direction, we're going to have the same thing. All right. So we're going to combine these equations together. So all I'm going to do is I'm just going to differentiate this quantity. This is Vx. So I'm just going to differentiate this by dx. And I'm just going to differentiate this one by dz, right? Because the original equation is just that 0 is equal to the first partial of Vx with respect to x plus the first partial Vz with respect to z. Now I think even today you can probably do this integral. I mean this differentiation. This isn't too hard, right? Like there's not even any powers here. These are all just simple things. So what's that going to tell us? Well, this is what I just said. What's going to be the change in Kx with respect to x? Well, if it's a uniform material, it could be anisotropic right now. If it's uniform material, it's going to be constant, right? So when I do this differential, that's the constants are just going to come out front. The minus signs can go away because I got a 0 on the other side. And I'm just going to have this very, very simple equation that the second partial of h with respect to x times the hydraulic conductivity in the x direction plus the second partial of h with respect to z times the hydraulic conductivity in the z direction is equal to 0. And what two laws have I applied? I want to use two things here. Continuity and Darcy's law. So the assumptions are that I have a saturated material, the volume's not changing. So this doesn't work for a soil that's swelling. It doesn't work for a partially saturated soil, but it works for a saturated soil where there's no volume change. Now, if the soil is homogeneous if the soil is, we've already assumed that the soil is homogeneous, because if it's not homogeneous, then I can't pull K out of the differential, right? But if it's isotropic, that means that Kx is equal to Kz. So if it's isotropic, I even get a simpler equation because the two K's are equal, and I can get rid of them. And this is Laplace's equation. Those are actually both Laplace's equations, but the simplest form of Laplace's equation is equation 4. A very common equation in engineering. It's the same equation that drives heat flow. So a lot of analogies in other places. Same same equation for electrical flux through resistive material. Okay, so let's talk about how to solve Laplace's equation. So we're going to talk about the graphical technique, which you all know and love and have practiced on the back of envelopes in the bar the night before your homework was due, I'm sure. So we're going to define a potential function. So the potential function is going to be a function of our potential for flow. And what drives flow? What's the potential that drives fluid flow? Hydraulic head, the total head, not the velocity head, not the elevation head, the total head. That's what we were talking about here previously when we're talking about head here. We're talking about the total head. It's not pressure does not drive flow, elevation does not drive flow, it's the two together. We're going to ignore the velocity head in soils because it's really small. It's like really, really small. It's like really, really, really small. So we can ignore the velocity head. And if you think it's just elevation, does water flow uphill? Anybody take a drink from a hose? Anybody drink from a garden hose? Right? Did you lie down on the ground below the spigot to get a drink?
Yes.
You lie like a leaf. Right? You pick that hose up and you turn it on and you drink the water out of the hose, right? Water was flowing uphill. Why was it? How could it be flowing uphill? Well, the pressure at the bottom was higher than the pressure. The total head at the spigot was higher than the head of the thing in your hand. That's why it was flowing that way. It's total head that drives flow, not velocity head. Well, velocity head is not in our equation. Not pressure head, not elevation head. It's a total head. Water does flow uphill. Okay, so a graphical solution is we need to define a potential function. So our potential function is going to define H. That's our potential, the total head. So we want to know H in the space that we're trying to solve this problem. We're talking about a two-dimensional world here so far. Remember, we're talking about XZ space. So any place around this space, I pick a point, I want to know what the head is at that point. I need to know what H is as a function of X and Z. We're going to call that the potential function. All right? So we're going to define that potential function phi as minus k times h. And why do we want to put the k in here? Because that's going to be our constant, right? And then there's got to be some constant to it because it's a potential function. So if I differentiate phi with respect to x, I am going to get minus k times dh dx, and that's just equal to the velocity. So that's handy. Right? So if I differentiate the phi function with respect to z, I'll get minus k times dh dz is equal to vz. So what is it when I take the differential when I differentiate something? What is that? We call that. We got a function and I take the differential. What is that graphically? It's the slope of that, right? So that's the instantaneous slope of that function. It's in two dimensions right now. So we're going to define a complementary function, which we'll call psi, which is going to be some g of x and z. And it's complementary. So it's complementary, which means it's everywhere normal to. It's everywhere normal to the phi function. So if it's normal to the phi function, the partial of psi with respect to z has to be negative the partial of phi with respect to x. That's what the definition of complementary is. These functions are always going to intersect each other at 98 degrees. And notice that that's minus vx. If minus phi dx is just k times dh dx, which is just minus vx. That just comes from this. Let's see, change color, dark blue. I'm just taking this and substituting it in here to get Vx. And similarly, I can write the partial of psi with respect to x is going to be the partial of phi with respect to z, which is going to be equal to Vz. That one's not negative. All right, cool. So these functions, this phi function and this psi function are orthogonal at every point. Every place these functions intersect each other, they have to be orthogonal. That's what we just said. So let's go on and talk about flow nets. So we're going to call lines where phi is constant, right? Phi is our potential function. So we're going to call lines where phi is constant equipotential lines, so lines of equal potential. And I can draw values of the equipotential line. So this is where phi is I is equal to some I, and this is where phi is equal to some value other than I. But along each one of those lines, the potential is constant. And so along every equipotential line, what is the potential for flow? Yeah, but what drives flow? Total head, right? So along an equipotential line, del phi, the differential of phi, has got to be equal to 0. Because if it's constant, right? If it's constant, then this differential's got to be 0, right? So there's no flow. There can't be a flow along an equipotential line because there's no change in the potential. So the equipotential lines have to be normal to the flow. If there's no flow in this direction, right, then the flow has to be normal to that direction. Right? The flow has to be normal to that direction. So we're going to call the psi lines of constant. We're going to call the lines where psi is constant flow lines. So we draw those in. Those lines are going to be, these lines are always going to intersect normal. I hope there's not any distortion in the, did it get distorted over? No, it looks pretty good. Those are normal. So if these two sets of lines intersect normally, and we know that the equipotential lines have to be normal to the direction of flow, what can we say about the psi lines? That the psi lines have to be parallel to the direction of flow. That's why we call them flow lines. If I put you in a little inner tube, a little donut inner tube, and I dropped you right here, you're going to be traveling right along that flow line. So we can have a graphical solution to our flow net. All we have to do is draw a family of lines of two. All we have to do is draw a family of equipotential and a family of flow lines, and make sure that every place they intersect are 90-degree angles. That's the general solution to our differential equation. Right? Differential equations. That's a general solution to. Oops, not there. That's the general solution to this differential equation. Is a drawing that has a bunch of lines on it that intersect at 90 degrees. Now, in addition to the general solution, what I have to satisfy to have the exact solution for a specific solution for any specific flow, any differential equation, you got to satisfy the general solution. Then what do you have to solve for? All the constants, which are your boundary conditions. So to have a solution to this that's specific to a specific problem, I need to draw a bunch of lines. I need to draw two families of lines that each family is always parallel to itself and they intersect at right angles, and I got to meet my boundary conditions. So these lines always have to be orthogonal. They have to meet the boundary conditions. Another requirement, which actually is related to boundary conditions, is that the aspect ratio of these this flow net that we're going to draw, this A over B, the ratio of the aspect ratio of each cell has to be constant. We don't actually need that to solve the differential equation. We need that for the way we're going to interpret the differential equation. Because if they're not constant, if the ratio of A over B is constant, then the relative change, the relative equipotential change between every equipotential line is the same, and the relative amount of flow in each flow channel is going to be the same. So it's a convenient way to do this. It doesn't have to be the same, but they don't have to. A over B doesn't have to be 1, which is the way we usually do it, but it does have to be constant. And obviously, it's a graphical solution. It's got to be drawn to scale. So if I can do those, if I can do those four things, I have a solution to my differential equation. And even a few decades ago, this was the easiest way to solve this differential equation. Okay, so we'll do a little flow net example. So the first thing we're going to do in the flow net is identify our boundary conditions, because we're going to start at the boundaries. So let's see, what's the easiest way to do that? I think I have four different boundaries in here. Right? This is a concrete dam that has a very low hydraulic conductivity, so we're going to assume it's impervious. I've got water on this side of the dam, and obviously the water is going to be flowing somehow from that side to this side because I got a low head here and a high head here. And this is a clay layer, and I have a sandy material in here. So this, all the flow is going to be in this material, and this is going to be an impervious boundary on the bottom. So you understand the general lay of the land here? Okay. So what are the boundary conditions here? What's the blue line? What are the boundaries at the blue lines? Yeah, they're. I'll give you a big hint. All the boundaries are either equipotential lines or flow lines. So what's the boundary condition along? If you're not sure, let's put a piezometer in there. I'm going to put a piezometer in here, right down to there. Where's the water going to rise to? Right up to the top of the lake. And I put one here. Where's the water going to rise to? Right up to the top of the lake. So every piezometer I put there right at the surface, the water's going to rise to the top of the lake, right? So what's constant along that line, that blue line? The total head is constant along that blue line, because that's how we, the height above the end of the piezometer, where the water rises to, is the total head. So that's an equipotential line, right? This is equipotential. What about on the tailwater side? I've got the same thing, right? I put a piezometer in here, water's going to rise there. Put a piezometer here, water's going to rise there. This is another equipotential line. All right. This one's pretty obvious. If I'm a molecule of water and I drop you right here, right at the corner there, how are you going to flow? I'm a molecule of water and I drop you right up against the dam here. Where are you going? You're just going to flow right along here. You're going to flow right over here. You're going to flow right out there. That green line is it's a flow line, right? This is a flow line. Not quite so obvious as this one at the bottom is also a flow line. But if you think about this thing being infinitely long, which really is, it's really infinitely long in these two directions, right? If you think about being infinitely long, if you were the poor son of a sailor that was stuck down here in the bottom, you're just going to be traveling right along the bottom forever and ever and ever and ever. So that's a flow line too. So now all I have to do is draw a series of flow lines and equipotential lines that meet at 90 degrees and meet the boundary conditions. What's the boundary condition? What's the boundary condition? If this is an equipotential, what can we say about the boundary condition there? It's an equipotential line, so what can we say about the flow lines at that point? Well, all flow lines are parallel. Well, they have to intersect here at 90 degrees, right? Right? And they have to be parallel to down here. So if you're going to draw a flow net here, so we know the flow lines have to be at 90 degrees here, we know they have to be at 90 degrees here, and we know they have to be parallel to one another. So the easiest way to start this flow net, if you look up here and down here, you see, well, these two lines are really parallel. So I know right in here my flow lines have to be parallel, right? So this is my first stab at this flow net. I'm going to draw a flow line in like that. And you've done this exercise, you're just going to start working it, and you're going to get frustrated, and you can have a beer, and you're still going to be frustrated. And then you're going to turn in something that's about half cooked, and your instructor is going to give you all kinds of marks on it, sure everything was wrong with it. And you're going to think, this is a stupid exercise. which is why we have the second half of today's lessons on numerical methods. Okay, but we're not going to draw flow lines. We're going to give you flow lines. So, but you notice that here is the solution to this. Notice these all intersect at 90 degrees, right? They all have the same aspect ratio, which is 1. Notice that if I draw a circle in each one of these, that it's tangent to all the sides. Okay, so this is what's important. What's important, I promise you I'm not going to ask you to draw flow nets, but I will promise you that I'll ask you to interpret flow nets. So what's really important about this is that you be able to understand the flow nets. So I put, so if this flow net is drawn correctly, if I put those two, I put piezometer, those two locations, what can we say about the water, the rise of the water in that piezometer? Yeah, this is, let's see if I go back to my colors. I was trying to keep my colors the same. This is a blue line. What kind of line is that? Equipotential. So these have the same potential. So the water in those two piezometers has to rise to the same height. Now I drew that it was rising above the height of the tailwater. Is that right or wrong? That's right, because the water is flowing from left to right here, right? So that there has to be a higher head at those 2 points than the equipotential line here at the tailwater, or else the water's not going to be flowing in that direction. And we know it's flowing in that direction. How high does it rise above the tailwater? What's this distance right here? What's this delta, don't do that, delta H there? Well, let's do it from this side. We're gonna answer that question here real quickly. So where's the height going to rise in these 3 piezometers? When the first one is going to rise up to the tailwater, the second one is going to rise a little bit less than that, and the third one is going to rise a little bit less than that, right? Because the water is flowing in this direction, right? Well, if we drew this flow net correctly, the change in head in each one of those is going to be the same. It's going to be little delta H, delta little h. I should have written delta little h over here. This one's actually going to be 2 times delta little h. That was a function of us deciding that the flow net was going to be drawn with all the cells having the equivalent aspect ratio. If we draw it so all the cells have an equivalent aspect ratio, then the change in head between any adjacent pair of equipotential lines is going to be the same, and the Q through any flow channel, Q1, Q2, Q3, and Q4 are all going to be equal. So if the drop between each pair of equipotential lines is constant, is equal to little delta H, we know what total delta H is. That's the total head loss. So little delta H is just got to be big delta H times the number of drops. It's not the number of equipotential lines, it's the number of drops. So how many drops are there in this system? Count them up real quick. How many drops? 10. All right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 drops. 11 equipotential lines and 10 drops. All right. Clean this up one more time. And so this is our equation for flow through the whole thing. This should be familiar to you. It's the total flow is equal to the hydraulic conductivity times the total head loss times the ratio of the number of flow lines to the number of the flow channels, number of drops. How many flow channels do we have? 1, 2, 3, 4. And times the aspect ratio. We like to draw these 1 to 1. And then W is just the distance, the width of the dam. W into the board. Or if you want to think of that, that's a Q per unit width, whichever way you want to think of it. Oops, is that it? Page up, page up. I guess that's it. Right, and this is all review, right? You all know this? Okay. If you don't, go learn it, because I expect that you already knew it. So I expect you, I'm not going to ask you to draw flow nets, but I'm going to expect you to be able to interpret them. And even when you're doing numerical solutions, it's helpful when you're doing numerical solutions to draw flow nets in them, because it really helps you to understand it. Okay, let's talk about transform sections. So it's very, very common that we'll have a case where the horizontal hydraulic connectivity is much bigger than the vertical hydraulic connectivity. We might have a homogeneous material, it's just anisotropic. They have a different property in one direction than another. It could be the same in all the space, it's just that it's got a higher horizontal hydraulic connectivity than vertical. If we have a layered system like the ones we looked at last lesson, but it's consistent across the whole site, then we really want to treat it, instead of trying to calculate the flow in each layer, it might be easier just to treat it as a homogeneous equivalent material with a hydraulic connectivity in the X direction that's higher than the Z direction. Very, very common. So we're going to talk about how to solve for that. Remember, when KH was not equal to KZ, the LaPlace equation was still good, but we have these two constants in there, and we can't drop them out now because they're not equal. So what we're going to do is we're going to use what's called a transform section to get this equation back to the equation that we had before. So we're going to replace X with X transform such that I get the same hydraulic connectivity. And what I'm going to choose to do is I'm going to replace X with the ratio. I'm going to replace KX by KZ such that I have, I'm just dividing through here by KZ, right? All I'm going to do is divide through by KZ. So now I have the partial of dH squared dx squared divided by kz over kx is equal to this partial. So that gets me pretty close to the right answer. And then I'm going to create this variable called x transform, that is just going to be the square root of the ratio of the two k's times x. Right? I'm creating a new variable, x transform. So what's the second partial of that? Well, the second partial of that is just going to be, right, this is, if I take this out, this is kz over kx to the minus 1/2, right? And if I take the second partial of this with respect to x, I'm just going to come out with this equation and an equivalent hydraulic connectivity, which is going to be the square root of kx times kz. So now what I have is I've got a new way to solve my equation. I now back to the simple Laplace's equation here, except I'm using this x transform. And when I go to do calculations for flow rates, I'm going to have to use an equivalent KE that's just the square root of the kx times kz. So the way we do this with flow nets is now we can solve our flow net. All we got to do is redraw our flow net in this new space, the x transform space. So this is an example of doing that. So here's another flow net similar to the previous one, and I've drawn the dimensions in here to make this clear. So that's 10 in the x and 10 in the z direction. And the horizontal hydraulic connectivity is 4 times the vertical. We've done some pump tests and we know that. Well, the first thing I'll do is determine my transform scale. So the transform scale is the square root of kz over kx. So it's the square root of kz over 4 times kz. Which is the square root of 1/4, which is 1/2. So now what I want to do is I want to redraw this figure to a scale where x transform is 1/2 of the original x. Right? Oh, and I got an equivalent hydraulic connectivity that's twice the vertical hydraulic connectivity. So now I'm going to draw a new flow net. Notice that my x scale here is now, half of the x scale up there. All I've done is redraw the whole figure with the scale of x half of what it was before. Now I'm going to draw my flow net, same flow net I had before. So that's the way it looks in the transform space. And then all I'm going to do is I'm going to go back and untransform that back into the original space. Whoops, that's not what I wanted to do. I'm just going to draw that back into the original space, and that's my flow net in the original XZ space. Notice that these things no longer intersect at right angles, but this is still the correct flow net. Those are still equipotential lines, they're still flow lines. The reason they don't intersect at right angles anymore is because I did this transform, and it's not really the same problem. So what we do is we're just going to take our anisotropic medium, we're going to turn it into an equivalent isotropic medium, and then if we want to figure out what's going on, we just transform it back into the original one. So it's just a graphical way to deal with anisotropic materials. And there's a really good example in your textbook too that you might like even better. All right, that's LaPlace's equation. And I think we'll probably accept the transform. Has anybody done transform space before? Yes, no? No. So that's the only thing that's new. It's a really good example. It's well discussed in your textbook, and it's pretty simple to do. So we're going to, we're going to get started, and I'll take a break someplace in the interim. Any questions about this?